Okay, hello everyone. Um, my plan for today is finishing the new sections, the introduction part. Hopefully can be finished today. If not, then maybe a little bit on Thursday. So before I'm continuing the sessions, I would like to have feedbacks on your quiz. I think I checked some, maybe 6, 7 papers. I think based on the time limit and the complexity of the question, I think you did very well. You did very well. From what I've seen, it's around, there's a few, maybe 40, but the rest is 60 something, 70 something. So I think that's pretty good for that kind of questions. I know that is, I think the problem is the time. Okay, so yeah, and also I mentioned in the Moodle that I would like to add some points from your homework too, at least 5% to 10%, okay? And I think it will be helpful for your result, quiz result. And yeah, I think I will finish the grading very soon. So on Thursday, if you'd like to know your score, please come on Thursday. I will deliver the result. So that's the some feedback for quiz 1. I will have another feedback later, so you can just wait for the end of the course. I will give you some feedbacks, and you can write something about the quiz. Yeah, I think that's just some notes. Okay, now we have seen, okay, in some way that in higher order, we are going through, especially in boundary value problems, when we limit in the first order problem, we have only one restriction, right? We only have initial conditions. But in higher order, we can have those initial conditions becomes more than one. So we call them boundary value problems. So we are actually seeing some. It can be having as many as it can for the solution. So we can have infinite many solutions. And we may have the solution only one, or we don't have any solution at all. We could have that. And we also discuss on the homogeneous equations, and this will be very important part, this homogeneous equation here. I will go through this homogeneous later again when we deal with the non-homogeneous one, because this will affect the non-homogeneous one. Okay? And there is some differential operators that we are going to look at. Maybe some parts later we are going to use this. So I hope you can see the how the equation will be, and I hope you are familiar with this also. It's actually the same thing with the ddx. We are going to change this with just capital D. Okay. And lastly, we discuss the superposition principle. So in summary, what superposition means, when we have y, y1, y2, y3 as our solutions, then the superpositions of all this y, it is supposed to be our solutions too. So y equal constant multiplied with y1 plus another constant, y2, and another constant, and until some k, they are also our set of solutions. Okay? That's what superposition principle means. Okay? So we are going to combine all the supposed to be solutions within within this long equation, that is also our solution. Okay, that's the superposition. Okay, now I would like to write some idea how these superpositions can be true. How does it happen? Let me write in the new page. So let the y1 and y2 solve the differential equations. Let me give you the equation. Is y double prime plus p of x y prime plus q of x, or maybe q with capital Q, like that, y, and then equal to 0. So suppose the y1 and y2 can solve this dE. Okay. According to the superposition principle, we are going to have y equal c1y1 plus c2y2. This is also our solution, or also solve dE. Okay. To prove this to be true, I think this is it's actually pretty simple. What we are going to do is we are going to just put the equations inside the dE, and then take the double derivatives and substitute. So substitute with all y with this c1y1, c2y2. So first we can prove that by sub the equations to the, okay. So we are going to have, I think we can write with different color, c1y1 plus c2y2 and double prime, and then plus p of x, and then c1y1, and then it's prime. So it is, the first is the second derivative of the whole thing inside, and then the right side is the first derivative, and then plus q of x, c1y1 plus c2y2. And this is supposed to be equal to 0. Now, of course, we can simplify, and we can write down, because the constant will still a constant, we are just consider the variable y. Okay? So we are going to have c1y1 double prime plus c2y2 double prime plus, this is p of x, and we are going to have c1y1 prime plus c2y2 prime, and plus q, and just write as it is. Okay. Okay, now we are going to combine all the C1 as one group, and C2, and C2 as one group. Okay. So we are going to grouping all this C1 and C2. So C1 and the same thing here. This is y2 double prime
plus p of x y2 prime plus y qx y2, and it's supposed to be equal to 0.
Now, looking at this two equations, it's going back to the original equation, which is 0. Okay, which is 0. Okay.
Because at the beginning, we said that the y1 and y2 can solve
The differential equations. So when we try to prove that this superposition also can solve this, now when we put inside the equation and we
rewrite and simplify and grouping all together,
we see that this is going to be 0 and this is also going to be 0 because y1 and y2 are the solutions. Okay?
at the beginning we said the y1 and y2 are solutions. Okay. So this is going to be 0, and this is proven that y equals c1 y1 plus c2 y2 also solves the differential equations. Okay. So, as a conclusion, any constant multiplied functions, if that is a solution, if you change the constant, it will not change the fact that it's always to be the solutions. Okay. So let me write here. Conclusions. A constant multiple y equal c. Let me write c1 y1 x. Okay. Of solution y1x of homogeneous linear differential equation is also a solution. Okay, so if you know the solution is y1 and you want to multiply with the constant, it's also a solution. It can be a solution also. And another conclusion is, I think from the previous one also, that the homogeneous linear differential equations always have a trivial solution, which is y equals 0.
Okay, now we are still talking on the linear, in the linear differential equations. And we already said that the constant, we multiply with constant, is also a solution. Okay.
So we are going to see the what we call the linear dependency. Okay. So the next concept is the linear dependent or maybe and linear independent. Okay. Okay, let me give you the definitions first. I think this. Okay. Now linearly dependent on some interval. If they are a constant, let's say C1 until Cn, and some constant, they are not all zero, such that if we plug in the C1 into the equations like we have in the superpositions previously, it is equaling to 0. So this constant can be any constant. Okay? So if we have, for example, we are going to evaluate whether some solutions are linearly independent or linearly dependent with each other, what we can do is we can take all of them and make it into this long equation. We can plus all together, and we need to find a combination that make them 0. If it can be 0, that is linearly dependent. If not, then perhaps it's independent. Okay.
Okay, this. Okay.
Like for example, if we have x squared and then 3x squared, I think it's pretty clear. Okay? Because the second one is a constant multiply of the first one. So it's supposed to be dependent. Right? It's supposed to be dependent. But for example, sine and maybe cosine, although they are quite similar in property, but they cannot be 0 in any way, right? They cannot be 0 in any way. So it's independent. Okay. But of course, you can have many ways to, like, this constant can be any numbers. So maybe you are given 3 or 4 functions, but you can make all the 4, you plus all together, multiply with any constant. When it's 0, then you can verify, okay, that's dependent. Okay, but if not, then perhaps it's independent. There are another way to find out or to determine the dependency. We call them using the determinant from, we call the method is Wronskian. Let me write them for you. Maybe let me give you an example for this dependency. Okay. Let me give you an example here. So let function 1 square root of x plus 5. Function 2 is square root of x plus 5x. And then function 3 is x minus 1. Function 4 is x squared. Okay. So observe that the whole functions here, 1, 2, 3, 4, is are the 4 functions linearly dependent or independent? So we can set the, we can check them, and we could write with this, and we can try with any constant. And you could check the constant equal to 0 if you would like to. So we could try, we could also, if we look at the f3 x minus 1, right? And we have this minus 1, this is plus 5. So perhaps we are going to multiply with the 5, constant 5 for the function 3. So we could rearrange this. We could rearrange this. And this is also still, we can consider linear dependent if, for example, if we check that we have f2 and then c1 f1x plus c2 f3x plus c4 f4x. Now f1 is square root of x plus 5. This is c3, sorry. f3 is x minus 1. So let's this c3 becomes 5. So we are going to have 5x minus 5. Okay. And then this is, let's say we just take 1 here. So square root of x plus 5. So we are going to cancel this plus 5 with minus 5. Okay. And then we are going to have square root of x plus 5x. Okay, so we could have this square root of x plus 5x, which is our f2. Okay, so the rest of the f4, the x squared, well, we could take the constant 0. We could take the constant 0. This is also possible. Okay, we could also rearrange all these 4 functions, and maybe one function of them is a combination from the other functions multiplied with a constant. That's also possible. So instead, adding all with, and then we let them all become 0, we can also try to rearrange the functions, and maybe we could think one of them will be our solution, not solution. It is the result of the combination. The result of the combination. So for some parts, this way to find a constant and then rearrange, find a way to make it 0, or rearrange the functions to make it with, and then the resulting one of the functions mentioned is one way. The second way is to use determinant. Okay, on some cases, the determinant will be very helpful, okay, especially if you have a function that cannot be really observed through the this method. Okay. Yes. Oh, sorry. So yeah. So they are linearly dependent on some interval if at least one of these functions is a linear combination of the other one. Okay. Well, if you have 3 functions, then when you combine these 2, can it be the other one? Okay. So you have some like trial and error, okay, to find out which one is the best way to prove. Okay. But of course, if the function is simple enough, I think this way is very, very simple and not really difficult to prove. Okay. But the solutions to differential equations, okay, if we know that we can prove the linear dependency through this way, and we can also make up the superposition principle, okay, easily, then perhaps the one thing that we need to cover is how about if we have linear independent solutions? That is one case that need to observe, okay, because the linear dependent, we can solve them and make it into our superposition principle, right? So we can leave them away, and okay, we already done that. So we are going to focus now on the linearly independent. Okay, so that's more interesting rather than the dependent. More problems, I mean. So solutions to differential equations. So we are going to look on the linear independent solutions of differential equations. Now to solve this using determinant in matrix. Okay. But we need to set up the arrangement for the determinant. Okay, what kind of functions we need to put on. It's called the Wronskian method. It's called the Wronskian method. And this Wronskian, we can, well, it can be proven for linear independent and dependent, but this Wronskian also important later when we deal with some techniques in, when we deal the higher order techniques, okay? Okay. Now we can have like functions, any functions, and the number of the functions can be any numbers. But what we need to set is this line is telling you that we need to compute this with the determinant. Okay? I hope you still remember determinant in matrix at least. We are going to cover a little bit matrix later after the midterm. Okay. Well, the midterm is supposed to be after we finish the higher order. That will be your midterm time. So we are going to set this function. Okay. The number of the functions f1, f2, f3. Let's say you have f1 and up until f3. Okay. So f1, f2, f3. Okay, that's the first row. The second row is the first derivative. f1 prime, f2 prime, f3 prime. Okay. The last row is f1 double prime. So we have secondary f2 double prime, f3 double prime. Okay. So the number of the last row, the number of derivative of the last row is n minus 1 of the total functions you have. So if you have 3 functions, you have 2. So you have second derivative. If you have just 2, then you have this 4, okay, this 4 arrangement. Okay. The way you are going to compute is you just compute the determinant. Okay. If you have these 2, then this is f1, f2 prime minus f1 prime, f2. Okay, the determinant. If you have 3 by 3, you are going to compute the 3 by 3 with the matrix. Okay. Well, I will try to involve some of the computations so we can review that matrix as well for computing the determinant. Okay. So what this Wronskian conclusions to our linear independent. So this Wronskian is telling you linearly independent if the result is not 0. So it will be linearly independent. If the result is 0, that means it's dependent. So let me write. And maybe I have the picture. Let me check. Oh. No. Okay, no. I think I will write here. Okay, let y1, y2 until yn be n solutions of homogeneous a linear nth order, so it can be any order, differential equation on some interval I. Then set of solutions is linearly independent. On interval I if and only if the Wronskian, we say the Wronskian with W like this, and then writing all the solutions up until yn is not equal 0 for every x in the interval. Okay. So let me give you an example. The example, I think it's quite complicated, the solution, but let me write example. Let y1 of x is cosine 2 ln x divided by x cubed. And y2, this is equal to x cubed. This is sine 2 ln x. So let this two be a solution, or are solutions of dE and interval solutions is from 0 to infinite number, but not include 0, because we are going to avoid the ln to be 0. Okay. I mean the ln 0, which means undefined. And from what we have in the differential equation, we already have y double prime, y prime, and y, and all the constant, they are having non-zero constant on the equations, right? So we have in order y double prime, y prime, and y. I think we can just directly go to the Wronskian and prove that this is linearly independent. So how we are going to prove? First is we are going to compute the y1 prime. So we are going to derive the cosine. So I hope still remember your calculus one. So this is a quotient rule. So I will directly take squared on the bottom. And then to help you remember, the quotient rule, said that we are going to have this, and this is f and g. So cosine 2 ln x is sine 2 ln x, and then multiply with the 2 ln x is 1 over x. So this will be sine 2 ln x multiply with 1 over x, or 2 over x, and then multiply with g is x cubed. So we are going to rewrite this and x squared. And we have negative, right, from sine. Okay, and then y2 prime supposed to be the same or similar oh, forgot to write the next quotient, sorry. Oh, why? What's happened? Oh. Oh. Wait. Let me just write again. Wait, this is interesting. Okay. Well, okay. Okay, minus, forgot to write this. 3x squared cosine 2 ln x. Okay. X power of 6. Same thing happened here. It's cosine 2 ln x, 2 over x, and this will be the x cubed minus the 3x squared sine 2 ln x. Yeah, it's quite long. Well, can you imagine if we take the Wronskian? If we take the Wronskian, then we are going to put the y1, y2, and then below them this y1 prime and y2 prime. We can find the denominator from that. But because we just take the interval from 0 to infinity, we can take any number x. We can take any number x, and then plug in first to make it simplified, and we can just evaluate the result. So evaluate the determinant of the result. So because we have ln, right? We have ln, and if we have ln1, it will be 0. So why not we are using the x equal 1 to make all the ln simplified. So take the x equals 0. So let me write here at x equal 1, sorry, x equal 1, we can write y1 is 1, right? y2 is 0, sine 0 is 0, right? And then y1 prime is, we can take x equal 1 here, this 0, 0, and then 0 here. Cos 0 is 1, 1, negative 3. So we have negative 3. And y2, where is y2? Here. We take 1, 1, it's 0, it's 1, 1, it's 2, it's 2, 0, so it's 2, it's 2. So we take the Wronskian from y1, 1 and y2, 1. 1, 0, negative 3, 2. And the result is 2 minus 0, right? So it's 2. It's not equal 0, which means that this is linearly independent.
So if you have the interval already, then you could directly choose some x from the interval. Well, the question can also be reversed. The question can be reversed. Maybe we need to find the interval to make the conclusions is dependent or independent. If you want to make it dependent, then you need to make it 0. You need to make the determinant 0, and you need to find x from there. Yeah, you can find as well. Yeah, but it's way more complicated because you need to at least check trial and error for some access. Okay, we will have a break up until here.
Okay, have a break. Okay, now we take the Wronskian, e with power 3x, and then e with power negative 3x. Okay. Now we are going to arrange the determinant. So e 3x, e negative 3x, and this will be 3. We derive one time, and negative 3 e negative 3x. And I think without any x to put in, we could find the determinant from this value, because we have 3x and minus 3x, which can be cancelled, right? So we are going to multiply this part and minus this part. Okay. So we are going to have negative 3, right? Minus 3, which is negative 6, which is not equal to 0, which is we can take this as a, or conclude this as we are having linearly independent. Oh, sorry. What's happened here? Okay, linearly independent. So y1 and y2 form fundamental set of solutions. So the general solution, we could write y equal c1e with power of 3x plus c2e with power negative 3x. General solution on interval I, or we could write the interval. It's for all x, right? For all x. Okay, I hope you still remember how to do the determinant for 3 by 3. Okay. If we need more review, maybe that will be maybe Thursday or maybe next week. We can have some review. But at least for 2 by 2, it's okay, right? For 2 by 2.
AD, this one minus this one.
Okay, next is we are going to jump to the non-homogeneous equations. Well, to begin the non-homogeneous, I would like to start with the particular solutions. So let the YP it becomes the particular solutions of the equations. Which means it will satisfy the non-homogeneous one. Okay. If we have the y double prime plus 9y equal 27, if I say that if y is equal 3, it's supposed to be works on this differential equation, right? If y, let's say let y equal 3, this will works perfectly, right? Because 3 is just a constant and its derivative is 0. So we put y and then it works perfectly with this differential equations. But of course, the problem is this is not the only solutions, right? But this is a particular solution that satisfy non-homogeneous. Okay, so we could say that this y equal 3, this is our YP. This is a particular solution. Now, because we have learned the homogeneous equations, the fundamental set of solutions from the previous one, and how to write the general solutions for homogeneous, now we can also write similarly with this non-homogeneous. So let me write here. If y1, y2 up until yk and let's say they are all homogeneous solution, homogeneous solutions on interval I, and yp, okay, is particular solution of non-homogeneous. Also on the interval I, then we can combine all those two. Okay. So y equal c1 y1 of x plus c2 y2 of x plus until k, and then plus the last part is the particular solution yp. Now this is also a solution. Also a solution of non-homogeneous. And we call this part is our general solution of non-homogeneous. Okay, so the general solutions will contain the homogeneous part and the particular solution. Now this homogeneous, we can also simplify, becomes, we can just call them a complementary function or complementary solution. Later I will always write below. So it's called the complementary function. So we are having the, let me write again the same general solution. And let me write Cn, Yn, x, and then plus Yp. Now we can write this, simplify the homogeneous equations with just y, c, x, so we can write simply yc plus yp. This yc is homogeneous, for not homogeneous. So non-homogeneous will have the homogeneous and particular solution. So whenever we are dealing with the non-homogeneous equations, the first thing we did is we need to equaling the solution, the equation with 0 to make it homogeneous, and find the proposed solutions from there. Okay. And then the second thing is finding the particular solution. So first, make it homogeneous, find yc, and then find yp, and then we can arrange the solution. So this has become the general solutions. And from this example, when I wrote the yp's, it's supposed to be like a single yp. But in truth, it can be more than one. And we could have the superposition yp1, yp2, yp3, and so forth. So we could have yc, yp. Yc is for homogeneous. Yp can be more than one, but we are going to write with the superposition. Okay? I will write later the conclusion. Yeah, I think that will be yeah, I will write the last thing, last section for today's class, the superposition principle. For non-homogeneous equations. So we are going to have more than one yp. So we have yp1, yp2, yp3, up until ypk, and k is any number. So let this yp be k particular solutions of non-homogeneous linear nth order differential equation. So this is on interval I, on interval and in turns this will corresponding to some k distinct functions g1, g2 up until gk, suppose yp is a particular solution of dE, so this will be an x, y, and plus gix. Oh, this is pi. It can be 1, 2, 3, where I is 1, 2 up until k. Then yp of x is equal yp1 of x plus yp2 of x plus plus pk of x. Then this ypx is particular solution of, we could write down this one time particular solution of this equal to g1x plus until gk of x.
Also point for all quiz, all exam, remember you can bring your calculator. Okay? Because I believe there will be some difficulty on at least the techniques for integral. Okay? That's this problem. So you can, at least your calculator will confirm whether it's correct or not. Okay? You have a process and you can confirm with your calculator. At least that for that. Okay? Confirm.